All right, guys, welcome back. We will be going over section 6.1. This is an introduction to set theory. I know we've talked a little bit about set theory already, so let's go ahead and refresh ourselves. A set is a collection of elements. It could be numbers, it could be dogs, it could be letters, it could be other sets. So set is just a collection of objects. This symbol, as we know, just means that X is an element of the set S. So, for example, 2 is an element of this set because this set contains the element 2. Another example, pi is an element of the real numbers, right? Pi is in the set of real numbers is another example. As we know, if there's a slash through this little E-looking thing, it means that X is not an element of the set S. So, for example, the square root of 2 is not in the set of rational numbers. Another example, negative 3 is not in this set because negative 3 obviously is not listed. Now, I mentioned just a second ago, we can have sets being in other sets. This is not something I don't think we've talked about. So, for example, consider this set right here. It contains 2 elements. It contains the element 1, and it contains the set containing the element 2. So we have 1 and the set containing 2 are the only 2 elements of the set. So what does this mean? It means that 1 is in fact inside the set because it exists right here. And it means that the set 2 is inside the set because it's right here. Now, kind of tricky, it also means that 2 is not in this set. You might think 2 does exist in the set, but it doesn't because the only 2 elements are 1 and the set containing 2. 2 is not one of these elements, even though it's deeper in. If you were to kind of keep peeling back these little set brackets, you would get to 2, but that's not how sets work. It has to be it has to be separated by a comma from the very most outer layer of the set. So 2 is not in this set, but the set containing 2 is. Okay, this is just a different notation for sets. I believe we've talked about this before, but to refresh your memory, if you see this bracket with X is an element of S, this line means such that P of X. This is just saying the set of all elements X in S such that P of X is true. The set of all elements X in S such that P of X is true. So, for example, if you saw this, the set of all X in the integers such that X is even, this is just the set of all even integers. So X has to be an integer and it has to be even. Therefore, this is just the set of all even integers. Another example, the set of all X in the real numbers such that X is bigger than 3. This is just the set of all real numbers that are greater than 3. Okay, subsets. This is something we definitely have not talked about. A set A is said to be a subset of another set B if all of the elements of A are also elements of B. This is the notation that we use. It's a little sideways cup with a line. It just means that A is a subset of B. So, for example, the integers are a subset of the rationals because every integer is also a rational number, right? Every element in the integers exists in the rational numbers. So you pick a number out of the integers, say 7. Is 7 also a rational number? Yes. 12 is an integer. Is 12 also a rational number? Yes. Every integer is a rational number, therefore the set of integers is a subset of the rational numbers. Another example with a finite case. If you look at this set contains 1, 2, 4, 6, and 7. This is a subset of this bigger set, which contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why? Because 1 is in here, 2 is in here, 4 is in here, 6 is right here, and 7 is right here. So every element in here is an element in here. Therefore, this one is a subset of this one. Very similarly to the in the set of notation, if you have a cross through it, it means it's not a subset. So this means A with this symbol B means A is not a subset of B. So for example, the set containing 1, 2, 5 is not a subset of the set containing 1, 2, 6. Why is that? Well, 1 is in here and it's also in here. 2 is in here and it's also in here. But 5 is not in here. So even though it contains some of them, it doesn't contain all of them, right? Because 5 exists in this one and 5 doesn't exist in this one, this is not a subset of this, right? In the same way, this subset is not a subset of the other one either, right? Because 6 exists in here and it's not in here. So neither are subsets of each other, but we were just looking at this direction. This way. Okay, another example, the real numbers are not a subset of the integers. That's obvious because you can find a real number that's not an integer. For example, pi is a real number, but it's not an integer. So the real numbers are not a subset of the integers. Okay, a set A is said to be a proper subset of another set B if A is a subset of B, but A does not equal B itself. So, and we didn't mention this, you can have this right here. Consider the set 1, 2. 1, 2 is a subset of the set 1, 2. Right? Because 1's here and it's in here, 2's here and it's in here. Therefore, this is a subset of this. So they can be the same. That's for subsets. Proper subsets means that they cannot be the same set. So they're subsets of each other, but they're not the same. To denote a proper subset, you don't have this little line. Kind of think of them as like less than or equal to's, right? This means like the equal to part. If there's no line here, that means A is a proper subset of B. So for example, 1, 2, 3, the set containing 1, 2, 3, is a proper subset of the set containing 1, 2, 3, and 4. Because A, it's a subset of 1, 2, 3, 4, and B, they're not the exact same sets, right? So, as an example, 1, 2, 3 is not a proper subset of the set 1, 2, 3, right? Because they're the same. And proper subsets have to have the condition that the sets are not the exact same. All right, so let's go through some common not misconceptions, common errors made when distinguishing between this element containment and subset notation. So, as we know, 2 is an element of the set 1, 2, 3, but 2 is not a subset of the set containing 1, 2, and 3. Why? Because, well, 2 itself isn't a set. Right? To be a set, both things have to be a set. So since 2 is not even a set, it can't even use this subset notation. So 2 is not a subset of this because 2 is not even a set. Okay, what about this? The set containing 2 is not an element of the set containing 1, 2, 3. Why? Because I don't see the set containing 2 listed in this set, right? We talked about that just a second ago. If the set containing 2 was in here, it would be an element. But just 2 is in here, not the set containing 2. So the set containing 2 is not an element of the set containing 1, 2, 3. However, the set containing 2 is a subset of the set containing 1, 2, 3, right? Because every element in here is also in here. All right, let's look at some nested sets. As we mentioned a second ago, 2 is not an element in here because just 2 doesn't exist in here. And 2 is not a subset of this because, again, 2 is not even a set. So 2 is not an element, and it's not a subset of this set. What about the set containing 2? 2 is an element here. The set containing 2 is an element here because I can find the set containing 2 listed as one of the elements. It's right there. Right? Okay. Is the set containing 2 a subset of this? No, because the only element 2 is the only element in here. 2 is the only element in here, but 2 is not in here. 2 is not in here. Right? 2 is in here, but 2 is not in here. So, it's not a subset. It's an element, but it's not a subset. So be very careful when distinguishing between is an element and subsets. Okay, set operations. We're going to talk about some new notation. The union of two sets, A and B, is a set of all elements that are in either A or B. That basically just means you're combining all of the elements of A and B and making it into one new set. So if you see this U, this means union. So you take all the elements in A, take all the elements in B, and just smush them in together into one set. So for example, if we have the set 1, 2, 3, and we union it with the set 2, 3, 4, you just put all the elements together, get rid of any repeats if you want. You don't technically have to, but it's standard practice to get rid of any repeats. We have 1, 2, 3, 2, 3, and 4. So push them all together, see what comes out. Mix them all together. So you just get the set containing 1, 2, 3, and 4. Another example. The set of all real numbers, x, such that x is bigger than or equal to 0. What is this? This is just all real numbers that are bigger than or equal to 0. So you could think of this as maybe interval notation. This is 0 to infinity, including 0. The set of all real numbers y such that y is less than or equal to 0, this would be all the real numbers less than or equal to 0. So you can think of this as that. So if we were to union these two sets together, all positive and 0 real numbers, union all negative and 0 real numbers, what do you get? Well, you get all the real numbers, right? You get all the positive, you get all the negative, and you get 0. That's every single real number. So you union it together and you get them all. Another similar concept is called intersection. The intersection of two sets A and B is a set of all elements that are in both A and B. So what do you do with intersection? You look at the elements in A, and then you look at the elements in B, and you say, what do they have in common? And those elements that they have in common, those are the intersection elements, right? So we denote intersection with an upside down U. It means A intersect B or A intersection B. So for example, if we look at the set 1, 2, 3 and we intersect it with the set 2, 3, 4, you just look at what do they have in common, right? They both have a 2 in common and they both have a 3 in common. So their intersection, and that's it, right? Not 1, not 4, yeah. So their intersection is just 2 and 3. Similarly, here again, we have all the positive real numbers, positive or 0. And then here we have all the negative or 0. If you look at the intersection between all the positive and 0 real numbers and all the negative and 0 real numbers, what do they have in common? Well, just 0, right? Just 0. The only thing these two sets haven't... Oh, this should be intersection. I apologize. Intersect. They only have 0 in common. So their intersection is just 0. Venn diagrams are very useful when trying to look at these. So let's look at a Venn diagram for union. Here, this circle is going to represent A. The circle represents all the elements in A for some set A. This circle represents all the elements for B. And the entire blue shaded region is their union, right? You look at all the elements in A, all the elements in B, and you include them all, right? So A union B you can think of as this diagram right here. You're including A and B, everything together. So what would intersection look like? Well, intersection, again, this circle represents A, this circle represents B. Here's all the elements in A, here's all the elements in B. Where do they intersect? Just right here. Here's all the common elements. This would be A intersect B, just this shaded region right here. Okay, so let's move on to two more set operations. We can talk about the difference, B minus A. The difference of B minus A is a set of all elements that are in B, but not in A. So let's look at an example. And we use the normal minus sign. Okay, so minus, it's a little different. It's similar but different. You take B minus A. So you look at all the elements here, right? And we're going to subtract all the elements here. So what goes away? Well, we have a 2 here, but we're subtracting this 2 here. So it's like this 2 goes away. This 3 also goes away. So we have 1 left over, and then we have this 4. If you have any extra elements at the end, you just ignore them. Okay, you're just looking at all the elements that are in this one, but not in this one. Right? So the only element in here that's not in here is just 1. So again, you can think of them as just canceling and ignoring anything left over on this side. And then whatever's left over on the beginning, that's the subtraction. So that's the difference between two sets. Another example, let's look at all the integers and subtract off this thing. What is this? This is the set of all integers x such that x is even. So these are just all the even integers, right? So if we take all the integers and we take away all the even integers, what's left over? Well, obviously, it's just all the odd integers, right? The set of all integers x such that x is odd. Yeah, so integers minus the even integers gives you just the odd integers. All right, one more. We're going to talk about the complement of a set. So some of you may have heard of complement before. The complement of a set is the set of a set A is the set of all elements that are not in A. So the complement is everything that's not in A. But it has to be relative to some bigger universal set U, and I'll explain what that means through these examples. Complement, you just do A like raised to an exponent C. This means A complement. A complement. Sometimes in other texts you may see it as A bar. That means complement a lot of the time too. But for our purposes, we'll be just doing A raised to like an exponent C. It means A complement. So, if we're looking at all real numbers, what is the complement of this set? The set of all real numbers x such that x is bigger than 0. So this is just all of the positive real numbers. And then we're going to take the complement. So what is the complement of all the positive real numbers? Well, it's all the negative or 0 real numbers, right? Yeah. So it's the set of all real numbers x such that x is less than or equal to 0. Another example, a finite case. Let's say that we are looking at this. So here when I say in R, this is the universal set. In this set, this being our universal set, like our outlying set, if we're looking at the set -2, -1, 0, 1, 2, the complement of the set -1, 0, 1 is everything that's not in here. So what do I not have? I don't have a -2, and I don't have a 2. So the complement is just -2, 2. Yeah. Yeah, everything that's not in negative 1, 0, 1. The only thing left over is negative 2 and 2. You can kind of think of this like subtraction almost. They actually are, complements and differences are related. In fact, A complement is just equal to whatever universal set you're looking at, and you subtract A away. You get rid of A. So Venn diagrams, right? If we have set A right here, the circle, set B right here, the set B minus A, you take everything in B, right? Here's B, but you get rid of the stuff that's in A, so this goes away, right? And you're only left over with things that are just in B, but not in A. So this would be B minus A. Okay? Here I thought of the universal set as this giant square, right? This outside square. And A is this circle right here. So A complement is everything that's not in A, right? So all the stuff that's in A would be here, right? But A complement is this blue region, everything that's not in A. And you can kind of see why this is just the blue shaded region is also the universal set minus A, right? It's like everything, but you take away A. Okay, so let's talk about a different notion. It's what's called the empty set. So sets contain objects, but what if you have a set that contains nothing? And I don't mean like it contains 0. I mean that it literally has nothing inside of it. Something like that is what we call the empty set, right? It looks like this. It's a bracket, but then nothing inside, right? 2 brackets, but nothing inside. This is the empty set. Instead of writing this, we usually write the empty set as a 0 with a slash through it. Okay, so that is 0 with a slash through it, and this bracket with nothing inside, they mean the same thing. They both mean the empty set. So again, note that 0 is not an element of the empty set. Again, nothing is in the empty set, not even 0. So for A is not in the empty set for any A at all, right? A in whatever domain you care. A is not in the empty set for every single possible A you could think of, whether it be animals or carrots or whatever types of carrots. I don't know. Nothing is in the empty set. Nothing is in the empty set. So where does the empty set arise? Well, let's look at this example. Let's consider all of the elements, all the real numbers, all x. So instead of all real numbers x, such that 3 is less than x and x is less than 2. Well, this is just the empty set, right? Because there are no real numbers that are bigger than 3 and less than 2 at the same time, right? Yeah, you cannot have something that's bigger than 3 and less than 2. Therefore, this set contains no elements. It has nothing inside of it, so it's equal to the empty set. Another example, let's look at all the integers x such that 2 is less than x and x is less than 3. This also is the empty set. Why? Well, because there's no integers that are strictly between 2 and 3, right? X can't be 2, right, because we have greater than 2. X can't be 3 because we have less than 3. And there's no other integers between 2 and 3. Therefore, this is also the empty set. All right, let's look at a couple properties of sets. If you have A intersect B, this is the set of all elements that are in A and in B. This will always be a subset of A. This will always be a subset of A. And let's go back to that Venn diagram. A intersect B. Yeah, you can see right here. A intersect B is this blue shaded region. And it's inside A also, right? This shaded region is inside A. So A intersect B is a subset of A. And similarly, you can see that A intersect B is also a subset of B, which I will get, right here. A intersect B is also a subset of B. Let's see. Okay. Another property. A will always be a subset of the union of A and B. And similarly, B will always be a subset of the union of A and B. So let's go back again to this Venn diagram. A is a subset of the whole union AB, right? Because this circle A is inside the whole shaded region. It contains some like outside points as well, but that's okay. It's inside the entire shaded region. And for the same reason, B is also inside the entire shaded region. So B is a subset of A union B as well. Okay, next up, transitive property. If A is a subset of B and B is a subset of C, then A is a subset of B. So let's do a Venn diagram with this. Let's say here's A. If A is a subset of B, so you can think of like A is in here and like B is on the outside, right? But then B is also a subset of C, so let's get C in here. You can see that A is also a subset of C, right? A is inside C. So if A is inside B and B is inside C, then A is inside C. That's exactly how subsets work as well. Here's a couple more properties of sets. If X is an element of A union B, if X is inside A union B, so A, B, if X is inside their union, then either X is in A or X is in B, right? Because their union is the entire shaded region. It's the entire thing. X lives here. I'm picking a different color. If X is, say, right here, right, then is X in A or is X in B? Yeah, in fact, in this example, X is in B. X could have been over here. In this case, X would be in A, or maybe X is in here, where it's in both. In any case, X is in A or X is in B. Okay? Here, if X is inside their intersection, if X is inside the intersection of A and B, so here's A, here's B. If X is inside the intersection, so here's the intersection, if X is in here, what does that mean? That means that X is inside A and X is inside B, right? See, X is inside A because it's in this circle, and X is also inside B because it's inside this circle. So that's what it means for X to be inside the intersection of two sets. It means it's in A and it's in B. All right, if X is inside A minus B, so here's A, here's B. This is different than the last example. Before we did B minus A, here we're going to do A minus B. So A minus B is a set of everything that's in A, but then you don't include what's in B. Okay. So if X is inside A minus B, it's like somewhere here, that means that X is in A, but X is not in B, right? X is in A and X is not in B. So yeah, there's no way for X to be inside B if it's inside A minus B. And lastly, if we look at A complements, here's the universal set. Here's A. Here's the complement. If X is inside the complement, that just means that X is not in A, right? If X is in the complement of A, then that just means X is not in A. Okay, so let's talk about some proofs, because of course we're going to throw some proofs into this section. Let's say A and B are two sets, and we wanted to somehow prove, maybe it's not so obvious, maybe it is, but we just want to prove that A is a subset of B. How can we do that? Well, the idea is you take an arbitrary element, call it X, and you take it from A. If you can show that that element is also in B, that means that A is a subset of B. Why? Well, so if we take an element from A, that element could have been literally anything. So since we're taking an arbitrary element, this element could be anything you want from A. And we're showing that this arbitrary element is also in B. That must mean that every element in A must also be in B, right? Because X is arbitrary. X could have been anything in A. Therefore, everything in A has to also be in B. Yeah, so that would mean A is a subset of B. So let's look at a proof with this. Let's have A be the set of all integers m such that m is a multiple of 4. So this is just the set of all integers that are multiples of 4. The set of all integers that are multiples of 4. B is going to be the set of all integers n such that n is even. This is just going to be all of the even integers, right? All the even integers. Or all the integers that are multiples of 2. Ignore my capitalization error. Then A is a subset of B. So if A is this and B is this, I claim that A is a subset of B. And this is intuitively, right? The set of all multiples of 4 is a subset of the set of all multiples of 2. So let's prove it. We're going to assume A is this thing and B is this thing, as we stated right here. And we're going to take an arbitrary element from A. So let X be an arbitrary element from A. And we're going to show that X is also in B. Well, since X is in A, and A is the set of all multiples of 4, the set of all integers that are multiples of 4, X must be a multiple of 4, right? Since X is in A, X has to be a multiple of 4. That would mean that X is equal to 4 times K for some integer K. Since X is a multiple of 4, it's 4 times K. Okay, so since X is equal to 4K, well, 4K is just equal to 2 times 2K, which means that X is equal to 2 times 2K. Well, that's just the definition of even, right? Being 2 times an integer, that means that X is even. So, X has to also be in B. So, we just showed that if X is in A, that means that X is in B. Well, since X is arbitrary, right? Since X was an arbitrary element from A, every element of A is an element of B. Therefore, A is a subset of B. So I hope that made sense, because we're going to do a little more with this. That's how you show sets are subsets of each other. What if you want to show, let's say that A was a subset of B, and B was a subset of A. What would that mean? Well, if you think of an analogous question, if A is less than or equal to B, these are just numbers, and B is less than or equal to A, that means that A equals B, right? Yeah, it has to be. We'll put and operator. If A is less than B and B is less than A, or equal to, that means A equals B. In the same way, if A is a subset of B and B is a subset of A, that means that A must equal B. So this idea we're going to use to prove that two sets are equal. If you want to show two sets are equal, you show that one is a subset of the other in both directions. So let's go ahead and do proof of that. Let's have A be the set of all integers m such that m is equal to 2a for some integer a. What does this mean? This just means that you can represent m as 2 times something. So this is just the set of all even integers again. Just it looks a little different. Okay, so a is a set of all integers that you can write as 2 times a for some integer a. B is going to be the set of all integers n such that n is equal to 2b minus 2 for some integer b. So b is just the set of all integers that you can write as 2b minus 2, where b is any integer, it doesn't matter what it ends up being. I claim that these two sets are equal to each other. So let's prove it. We will show that a is a subset of b, and b is a subset of a. So let's start with a being a subset of b. So we'll have two parts to this proof. Here's part 1. A is a subset of B. So to prove that A is a subset of B, we're going to take an element from A and show that it's in B. An arbitrary element, right? So let's have X be an element of A. That means that X is equal to 2 times A for some integer A, right? So X is just 2 times something. Now, X is equal to 2A, and 2A is equal to 2A plus 2 minus 2, right? So all I did was add 2 and subtract 2. Okay. I'm going to group these two together and factor out a 2. And I get 2 times A plus 1 minus 2. Now I'm going to introduce B now. I'm going to let B equal A plus 1. All right, so this is just going to be B. So that means that X is equal to 2B minus 2. Oh, so X is in B, right? Because X was written as 2B minus 2. So since X was an arbitrary element from A, and we showed that it's also in B, that means that A is a subset of B. Great, so we have one direction down. Let's go the opposite direction. So part 2, let's show that B is a subset of A. I'll just use a different, you could use X again, I just wanted to go with a different letter. Let Y be an arbitrary element from B. Okay? Then Y can be written as 2B minus 2 for some integer B. Now, see, I should have kept it as an X. Y is equal to 2B minus 2, which is equal to 2 times B minus 1, just factoring out a 2. Let's have A equal to B minus 1. Oh, and by the way, since we're breaking this proof into 2 different cases, it's okay that I'm reusing A and B to mean 2 different things. They're kind of like local variables. So I'm thinking there's 2 different parts. Let's have A equal to B minus 1. Then X could be written as 2 times A. Again, X, Y. Y could be written as 2A, because B minus 1 is just A. So, Y is an element of A. So we show that if Y is in B, then Y is in A. Therefore, B is a subset of A. Since A is a subset of B, and B is a subset of A, it must be the case that A and B are the exact same set. So that does it for this one, guys. Next time we are going to continue on set theory. So we'll finish up 6.1 and we'll tackle 6.2. And yeah, I will see you next time.